Hello again. In the last video we stopped where we ended up with this equation here, where we have this part here is a constant and this part here is it is time dependent because x is time dependent and v is time dependent. Okay, and we said that we are going to derive with respect to time on both sides, right? Let's start deriving each one by one. So first, d over dt for half kxm squared. We said this is a constant, so the derivative of a constant with respect to time is simply 0. Okay, so this part here is going to be 0. Then d over dt for half k x squared equal. So half and k are constants, so we push them outside. So half k d over dt x squared. We know that when we're deriving x squared, so let me write it as a note up here. Let's choose some nice color here. So the derivative of x squared dt is the exponent here 2 times the function x with the derivative of x. Okay, it's the same thing as what's the derivative of f squared of x? It is 2 f of x f prime of x, right? Let's do the same here. So half k d over dt for x squared, that is half k x times 2 times dx over dt. Okay, 2 will go with 2, we're left with kx. So d over dt of half kx squared equal to kx dx over dt. Okay, let's put a rectangle around this. Now let's continue with the other part. What's the derivative now of half mv squared? So put a star here. D over dt half mv squared. Half and m are outside, the same thing that we did out like up there. dv squared over dt, that is half 2 will be the derivative of v squared is 2v dv over dt. It's the same thing as up here. Derivative of f squared of x is 2 f of x f prime of x. And if you are familiar with the other notation, let me write it here, which is u squared prime is 2 u prime. I think you're familiar with this more. Okay, this is what we are using here. When we say u prime, we're meaning du over dt. Okay, it's the same thing here. It's the same thing here. Half m, that's because it's a constant, and the derivative of dv squared over dt is 2v dv over dt, that is v prime. Okay, let us write it down in a better way, and then we are going to put a rectangle around it. So d over dt, d of half mv squared equals to, this goes with this, mv dv over dt. Let us put a rectangle also around this one. Okay, now let us plug in every value in the new equation. So if we derive this whole equation with respect to time, we're going to end up with 0 from this part, kx dx over dt from this part, and mv dv over dt from this part. Let's see what we are going to have. So let's use a nice color. 0 equals this one here, kx dx over dt plus mv dv over dt. Now, how can we play with this equation to get like a prettier one? Let's move to another page and play a bit with the equation. So again, look, I'm going to put 0 on this side and put the other part on the other side, so it's going to look better. Okay, so k x dx over dt plus mv dv over dt equals to 0. Now, dx over dt, we know that that is simply v, right? It is the velocity, v. Or we can say that it is x prime, right? Because the velocity v is dx over dt. It is the derivative of x with respect to time. It is simply x prime. And dv over dx, it is simply the acceleration, right? Which is v prime. And v is actually x prime. And v prime would be x double prime. It is the derivative of x 2 times. Let me show you. The derivative of x once is the velocity. The derivative of x twice is the acceleration. So we're doing fine. Let's rewrite this equation in terms of x prime, and x double prime. So we're going now to plug in our different way of writing things. So k x and dx dt, we're going to write it as x prime plus mv dv over dt is x double prime, and v, we knew that v is x prime, so we can actually write it as x prime. So x prime and x prime, we can cancel both of them. What we ended up with is kx plus m x double prime equals to 0. We can make it look a bit more decent, where we will have x double prime without any coefficient plus k over m x, just x without prime, equals to 0. Okay, so the equation that we have is x double prime plus x over mx. If we look closely, this equation, it has a function which is x and the derivative or the double derivative of the same function, which is x double prime. When we have an equation that has a function and its derivatives, we call it a differential equation. I'm not sure if this passed with you in your math classes, but when we have an equation with a function, I'm telling you about x as a function because actually x is x with t. It's a function of time. Okay, so x is a function. We have x and the derivative of x. It's not the derivative once, the derivative twice. It is a differential equation. Now, because the derivative we have here is not the first derivative, but it's derived twice, we call it a second order differential equation. If let's say we had x prime here, not x double prime, it's going to be a first order differential equation, but because we have x double prime, we call it a second order differential equation. That's the name of this equation. It's a second order differential equation. Let's put it inside a rectangle, a pink rectangle. So it is a second order differential equation. And second order differential equations in general, they have forms. This second order differential equation is of this form. Let me write it in orange. It is orange here. It's x double prime. Oh, why it's turning like this? No, like this. It is x double prime plus this thing here, k over m. K is a constant, the mass is a constant, so k over m is a constant. We call this constant omega 0 squared. Okay, it is omega 0 squared. This is x equals to 0. Now, why it is squared, why it's omega 0, that's just how we name it, because omega 0, what's the meaning of omega? It's the angular frequency. If you remember from last year when you took rotational motion, the angular frequency is denoted by omega 0. This equation here, the equation that we have here, it describes the oscillation of the body. So let me go back here. It's an oscillatory motion. It's from back and forth. So it has a frequency. Omega 0 is just the angular frequency. For now, I just want you to take it as it is. X double prime plus omega 0 squared, x equals to 0. That's our equation. Let me put another rectangle. Okay. And omega 0 squared equals to k over m, right? Then omega equals radical k over m. We have seen this before. If you remember when we were trying to find the velocity of the mass, this part here, or this thing here, it showed before. Okay, so remember when I told you in class to pay attention to this radical k over m, and it's the frequency, it's the angular frequency. So it showed here. And this equation, x prime plus omega 0 squared, x equals to 0, it's the equation that governs what we call the simple harmonic motion of a horizontal elastic pendulum. And let me repeat again. This equation, it governs the motion of, or the simple harmonic motion, the simple harmonic motion of a horizontal pendulum.